So hello everyone, my name is Anthony. Today I'm replacing Abby that generally hosts events for the Java London community. I am an associate at Java London community. Other than that, I'm also part of several other initiatives by RecWorks, like the Meet a Mentor group and the Aspiring Principles. So I'll just be posting a link about some of our communities, and everyone that is interested is free to join. I'm here today to introduce our host, James Easton. James is an architect at Amazon AWS, and he is going to talk to us about serverless event-driven architectures on AWS and how to use like AWS components to build next-gen applications, like scalable event-driven applications. So James, take it away.
Thanks, Anthony, and good afternoon, everyone. So yeah, as Anthony said, I'm James Easton. I'm a cloud infrastructure architect at Amazon Web Services, and today I'm going to talk to you about building event-driven architectures. There should be some time for questions at the end, so anything that comes up as we go along, if you want to just pop it in the chat. I can't see the chat at the minute, but then I can answer them as we get to the end of the presentation. So yeah, let's get to it. So it's estimated that our brains process 11 billion bits of information per second, and that's a lot of data. When it comes down to it, our brains are just giant event consumers. So they're constantly taking in events and making decisions based on what we receive from the environment. All our senses are sending data to our brain, and some of which we choose to use based on previous experiences, and some of which we choose to ignore. If I touch something, then my fingers will send a touched event to my brain. If that was something hot, my brain might react and make my hand move out of the way. But my body's reactive. It isn't wasting energy reacting to events that it doesn't need to care about. At a higher level, as humans, we love stories. We like to rationalize out things. It's based on things that happen. You know, this thing happened that caused this thing to happen. And then based on them two things combined, we might then choose to do something and react to that event. So if you think of a bank statement as an example, all a bank statement is a log of the events of the transactions that you've spent. And as humans, we can look at that log of events and realize that we've spent all our money and we need to wait till we get paid to actually buy anything else. So what I want you all just to do for a second is just to close your eyes and just imagine you've walked into your favorite pizza restaurant. So you go in and you place your order, and after you've placed that order, interesting things start to happen in the background. So you watch as the base gets rolled, your toppings are added, and the pizza's then baked, and at each point your hunger's increasing, but you're not actually doing anything to react to them events. And there's only actually one event that you care about, which is your order being boxed and your pizza being ready to eat. Now, I realise talking about pizza at 1 o'clock in the afternoon probably means I've lost some of you for the next few minutes thinking about pizza, but just try and focus back in for a second. Now, imagine a world where your systems are as observable as that situation and as extendable, where the events that happen in your system and the events that come out of the business processes your system's working with are treated as first-class citizens, and other components of your system are just reacting to them events as and when they need to. And that's where event-driven architectures come in. So I, like a lot of you, I imagine listening now, I'm a developer at heart. And whenever I hear about a new technology or a new pattern, I find myself behaving a lot like a magpie. There's a new shiny thing and it immediately takes my fancy and I want to drive straight in to the technical details. But what I've learned over the last 10 or so years is that it's valuable sometimes to slow down and just take a step back and actually understand the why. So why do we need event-driven architectures? And to talk about that, I actually want to talk a little bit about distributed computing. So the fallacies of distributed computing were first proposed by Peter Dush and others at Sun Microsystems. And what these fallacies talk about is false assumptions programmers who are new to distributed computing make. So, if you're a programmer working on a single process application, you might make a method call, and that all happens within that one process. But once you introduce a distributed computing, the network starts to have there's a lot of things that start to have an effect on what would appear to be a simple method call. So I've highlighted 5 of the fallacies there, and they're the ones that are really quite important. As you start to move to a microservices architecture and you make services smaller and smaller, and you start to get more and more and more amounts of services, these network interactions become really important. And it's absolutely vital to design an architecture that minimizes that latency to meet the performance, but also handles the realities of networking and of distributed computing. And coupling is a really important part of that. If you imagine a system where there was just 2 services, then that coupling probably isn't as much of a problem. Service A just makes a call to service B, and service B responds in a synchronous manner. But again, as you start to increase these number of services and increase the number of interactions, if everything was communicating synchronously over a network, and we know that the network's not reliable, then that starts to cause real problems when you get to really large scale distributed systems. So now that we've got a little bit about the why, what actually is an event-driven architecture? Well, an event-driven architecture uses events to trigger and communicate between decoupled services. Event-driven architectures commonly have 3 main components. There's event producers, there's event routers, and there's event consumers. So a producer will publish an event to a router, the router will filter and then push that event to various consumers. And the benefit is that producers and consumers can be scaled, deployed, and updated completely independently. And they don't actually need to communicate directly with each other. All the communication is by a different mechanism. But just to level set before we get too far into the actual architectures, let's just define what an event is. Well, an event's just simply that there's been a change in state to a system that's happened in the past and now can't be changed. So it's something that has happened, past tense. And the traditional viewpoint of a lot of architecture is that data is the center of any system. But with an event-driven architecture, we kind of flip that around a little bit and we make events the center of the universe. So events are the key part of the business that drives everything that happens. But even with events, we still need to move data around the system. And that's where we've got 2 types of events that we commonly see. We've got sparse events and we've got what we call full state descriptions. So a sparse event is more like a notification. It just contains the bare minimum information related to the event that's happened. Whereas a full state description contains all possible information. So if we think back to our pizza restaurant, an order placed event might include what's been ordered, the delivery address, the cost, the customer, the order number. There's a whole bunch of different things that will get included. And now there's pros and cons of each type of event, and not least the size of the data being transferred. So to start with sparse events are really great because they're extremely lightweight and they're really, the cost of moving that data around the system is relatively small. One of the downsides is that when consumers receive the event, they might need then to communicate back to your service to actually get more detail. Now, if you imagine a completely decoupled architecture where no services know about each other, as a producer, we have no idea how many consumers are going to use that event. So if at first you've got a relatively small system and you maybe only have a handful of consumers, that might not cause a problem. But as your number of services start to grow exponentially, I've seen situations in the past where we've ended up in the place where a consumer publishes an event and then takes itself offline because all the people consuming that event then come in and hammer it with requests to get additional data. So that's something to be aware of if you're using more sparse events. The opposite to that is the full state descriptions. So they obviously negate that problem because you're sending all of the data with the event. And then the consuming service can just choose to ignore any pieces of information it doesn't need. The problem here comes with the schema of the event because again, as a publisher, you've got no knowledge of which pieces of data the consumers are using. And that makes making changes to your schema really difficult. Every change needs to be backwards compatible because you've got no idea what pieces of data are being used and which aren't. So although the example on screen here is in JSON, just because JSON is a nice, easy format to read, from experience, I've actually found a more strict data transfer format like protobuf, for example, is better if you're going down the route of full state descriptions, because you can then enforce that schema and enforce that backwards compatibility as part of the protocol. So now we've kind of level set of why we need event-driven architectures and what we need. So we'll actually start to get into some technical details now. So we've talked about these events, and these events are first-class citizens, but obviously events don't exist in a vacuum. They need to communicate with other events and actually achieve business goals. And that's where orchestration and choreography come in. So first I want to talk about orchestration. So orchestration is something that happens within a business domain. So you can think of orchestration like a complex workflow within a given domain. So let's just imagine a business process for a domain as part of our pizza restaurant. So an order might come in, and there's somebody reading that list of orders come in, and then they pass that on to one of their colleagues who's actually in charge of seeing if that order can be created. So they might first check the stock to see if all the ingredients are available to create that order. And then they might even check with maybe the delivery drivers to see if there's a delivery driver available to deliver it. And if all that is achieved and okay, then the order will get created. Now, if you were trying to write this in code and you were trying to build this workflow, obviously there's a lot of different things that can go wrong and a lot of different situations and errors and problems that you need to try and write into your code and write into your process and handle. If it's a human doing the job, it's easy because humans can deal with that, but code needs to be written to handle all these different scenarios. And that's where a service like AWS step functions come in. So step functions is a low-code visual workflow service that developers can use to build and orchestrate distributed applications. And the workflows manage failures, retries, parallelization, service integrations, and observability. So you as the developers can just focus on them discrete pieces of business logic, and step functions can be used to stitch it all together. So you can compose workflows from over 200 AWS services, and step functions maintains the state of your application during each execution. And that includes tracking what step of execution it's in and storing the state as it moves between stages in the workflow. That means you don't have to manage the state and worry about data stores or building state management and retry logic. Step functions handles all of that for you. So step functions are built using what's called Amazon States Language, or ASL. That's primarily defined in JSON or YAML. But you can also build workflows using the AWS CDK. So the CDK, if you're not familiar, it allows you to define and deploy AWS infrastructure using programming languages of your choice, one of which is Java. The other way to define workflows, if I just jump back a slide for a second, is as of the end of last year, the step function team actually released what they're calling the Workflow Studio. And that is a drag and drop interface for building workflows. So you can build your workflow, build your retry logic, build your paths, all with a drag and drop interface. And then you can export that from the designer into Amazon States Language. And then you can put that JSON file into your source control repository, for example. And you can use that, and you can use all the good development practices and source control and release things that come along with good development practices. Once an execution of a workflow has ran, you can actually then go into the console and monitor that. So the image on the far right here, that's an execution of a workflow. And as you can see, you can actually trace where that workflow went. And at each individual point of that, you can see the data that came into that step and the data that came out of that step. And you can look at all the logs along with it. So you can actually go in and visualize how your workflow was executed after the fact and use that to maybe make improvements. So I talked before about the 200 services that step functions integrates with, and there's two types of integrations with step functions. So the first is what's called optimized integrations, and they're direct service to service integration. So that may be your workflow calling a Lambda function, and I'll talk more about Lambda later. And there's 17 different AWS services that are integrated natively. Towards the end of last year, they also introduced the AWS SDK integrations. And what that means is that step functions can now use the AWS SDK to integrate with 200 services, and that's over 9,000 API actions. And that's all native to step functions. That means you as a developer don't need to write any glue code, and that allows you to build, sentiment analysis workflows, or maybe image recognition workflows, and all the error handling and retry logic and the different states, all without writing any business logic or any custom code. You define all that in ASL. So it's a really powerful services step function. It's actually probably my favorite AWS service just because of how powerful it is. So if we now look at that same business process, but using step functions, it works in broadly the same way. So the order would still come in, and what the order processing would do would just be to trigger the step functions workflow, and that then acts as your orchestrator. So your step functions workflow might talk to the inventory manager, it might talk to the delivery service, and then if the happy path is complete, it would then go off and maybe raise an order created event that it can then pass on to other services. But the beauty here is that, let's say, for example, the delivery manager couldn't be contacted, you can build into your workflow retry logic. So you could say retry 3 times maybe, and if after three retries there's still no success, then fall back and follow a different path and do some different logic, maybe notify somebody or send a push notification to somebody's mobile phone. And that's where step functions gets really powerful. It allows you to define these complex business processes, but using a low code, no code interface. So that's within a business domain, that's orchestration. And it's all well and good having these separate domains that have all got these orchestrated workflows. But as we all know, no domains in our systems exist independently. At some point, these services will need to collaborate with each other. And that's where choreography comes in. So publishers of events are just responsible for sending events to a well-known location, a centralized location, and the systems interested in receiving them events just subscribe to events from that same location. So with our pizza domain, again, there's an order created event published, and the kitchen is just interested when there's a new order being created, because then they need to go and actually create that order. And these services still don't need to know anything about each other. All they need to be able to talk to is this centralized location. And that's where we need something here to handle that centralized processing of events. And that's where Amazon EventBridge comes in. So Amazon EventBridge is a serverless event bus that makes it easy to build event-driven applications at scale. You can ingest, filter, transform, and deliver events to sources without writing any custom code. And as it's a serverless service, there's no service to provision or patch and manage. You don't need to install, maintain, or operate any software. And EventBridge just scales automatically based on the number of events that are being ingested, and you only pay for the number of events published. It's got built-in distributed availability and fault tolerance, and it even has a built-in archive and replay capability, so that if you have a edge case problem that goes wrong, you can actually go in and replay that same series of events from old events. So it's a really powerful service. So EventBridge is directly integrated with over 130 event sources. So that includes other internal AWS services like S3, custom events that you publish from your applications, but also, and this is one of the really interesting use cases, a wide range of SaaS applications, including Datadog and Zendesk as a couple of examples, but there's a whole range of SaaS providers that can publish events directly into your systems, and then you can then choose to react on them events with custom business logic. When it comes to the targets, there's over 35 different targets that can be defined using rules created on EventBridge. And then so when the events come in, you can filter the rules. And if a rule matches an incoming event for a given event bus, you can then route that to a target. And that target may be Lambda, it may be step functions. So you could trigger a step functions workflow from EventBridge And all of that, again, is without any custom code and without any code that you've written. That is all native service integrations. So as I'm sure you've probably got your head around now, that orchestration and choreography work really well together. So sticking with our order processing for our pizza restaurant, a request may come in through an API, and that then kicks off the step functions workflow. The step functions workflow does all that, checking the inventory, sorting out a delivery driver, and once all that's confirmed, it would then publish an event onto Eventbridge. And from there could be any number of consumers listening to that. You know, let's imagine there's a kitchen service, maybe a loyalty point service, maybe a customer reviews service. And let's say down the line, we want to add an additional service to do something extra. All we need to do is just hook into that same order created event that's being published. And each of these services may go on to raise more events, and then events that get raised may go back to the order management service. You know, throughout all of that though, there's no direct coupling between these services. They're all completely independent and they don't need to know about each other directly. So that kind of covers the fundamental building blocks of event-driven architectures. So we've got internally within a domain, externally, we've kind of defined what an event is. But what we've covered so far is kind of the movement of events. And what I want to talk about now is a bit more specifically about how events can be stored durably and how AWS services can be used to ensure that events don't get lost and to distribute them as you need to. And for that, I want to talk about message channels. So message channels are a model for communication, basically. And this may sound pretty similar to some of the features of Eventbridge, but there's a couple of key differences with some of the message channels I'm going to talk about, which I'll cover when I get to them. And the first of which is a queue. So a queue can just take incoming event data and it will durably store it for processing. A queue differs from an event bus or event bridge in that durability. So a queue will store the message and its content to the point in which something picks it up and processes it. So how that kind of works in practice is that a sender would push a message onto a queue. The message, and each message that lands on a queue is processed by a single receiver. And commonly each of these receivers would be configured to only process a certain type of events. So in the diagram, events of type A, B, and C all land on the same queue, but they're all processed by one single receiver. Now, this is really good for scale. Let's say we started to get a backlog of type A events. We can just add more type A receivers, each of which will only ever process one event. Once we've got through that backlog, we can then start to turn off some of these instances. And queues can also help to flatten loads. So a common use case we see is for spiky writes to a database. So instead of your application communicating directly with your database, which commonly is a bottleneck once you get to large scales, your application can communicate with a queue, and then that queue will durably store your data, the information intended for the database, and you can have maybe a receiver that takes that information and puts it to the database in batches, and that keeps a really nice level load to your database that's really quite predictable. So the second type of messaging channel is publish, subscribe, or pub sub, and this is the one that's most similar to Eventbridge. And how that works is you still have a producer publishing events onto what is commonly called a topic. And the difference with pub sub is that every message is delivered to every single subscriber, as opposed to the queues, which is one event to one subscriber. And that makes buffering and scaling your consumers for a pub sub model quite difficult, because every event that comes through is going to go to every single current subscriber, and that can add some challenges when it comes to scaling and buffering. So to get AWS specific now, there's two cloud native serverless services we have in this space, and they're Simple Queue Service, or SQS, and Simple Notification Service, or SNS. So to start with SQS is a fully managed message queuing service. It's actually also the oldest AWS service. So SQS was released in November 2004, and it offers two types of message queues. So the standard queues, which offer nearly unlimited throughput per second transactions, best effort ordering, and at least once delivery. And that's important, at least once delivery. The other type of queue is first in, first out queues, or FIFO queues, and they're designed to guarantee that messages are processed and delivered in the exact order they are sent. Because of that, the throughput's a lot lower, about around 300 transactions per second, with the trade-off being you've got that guaranteed at least one delivery. So SNS is a fully managed messaging service for PubSub, and it's intended for high throughput, push-based, many-to-many messaging, and it integrates with a whole range of other AWS services. It also supports app-to-person notifications, so things like emails or SMS or mobile push notifications. And like SQS, it supports standard and first-in, first-out topics with similar numbers and similar restrictions around throughput. Now, I'm sure you're thinking now that SNS sounds a lot like Eventbridge, and it does often cause confusion around which to choose in a given scenario. And there's a couple of key differences. The first is the SaaS integration. So if you've got a requirement to integrate with a SaaS provider, then Eventbridge is a more logical choice because of these pre-built integrations that Eventbridge already has. The second, and probably my favorite feature of Eventbridge actually, is what's called schema registry. So schema registry makes it easy to discover and manage open API-based schemas for your events. So Eventbridge can automatically infer the schemas of your events as they are flowing through the Eventbridge, and they can display them as a registry that people can go and look at. On top of that, you can also generate code bindings directly to your IDE from Eventbridge, and that's for type-safe languages like Java. So if you imagine you've got a new development team starting to build a new feature, they could go to Eventbridge, to the schema registry, look at the events and think, oh, I want to use the already created event, and then generate some code bindings directly to Java, directly to their IDE, and start working from what they know is a schema that's going to meet the right criteria. The third difference really between SNS and Eventbridge is the number of subscribers. So standard SNS topics can support up to 12.5 million subscriptions per account, whereas Eventbridge only supports 300 rules per event bus. And that's quite important to, it's quite an important difference that, if you've got a really high scale with lots and lots and lots of subscribers, that may push you more towards SNS than Eventbridge. Now, it's important with both SQS, SNS and Eventbridge is that we commonly see use cases where customers are using a combination of all three. It's not, I'll use Eventbridge and not use SNS. All these services integrate really well together and work really well together. So within your systems now, you've already got some form of PubSub or a queue-based service, like, for example, RabbitMQ is one I commonly see with customers. AWS also has Amazon MQ, which is a managed implementation of RabbitMQ or Apache ActiveMQ. And what I mean by managed service is that AWS takes care of all the undifferentiated heavy lifting around the operations of the service, which leaves you as the development team to only worry about your code and how you interact with them services, instead of having to manage the cluster of servers that you're using to run your RabbitMQ cluster. And that is quite a good step into cloud-based, and some of the benefits you get from the cloud is moving to a service like Amazon MQ, because you can keep your existing code the same and just point it at a different location. So a common pattern we see with SNS and SQS is the fan-out pattern. So SQS and SNS have a native integration which allows for you to easily configure communication between the two services. So your producer would simply publish all of its messages to an SNS topic, and then SQS queues can subscribe to that topic and pull data onto the queue, and then your individual services can then process that backlog from the queue. So if we think back to the fallacies of distributed computing around the network problems, if you're a producer publishes an event to SNS and that then goes into SQS, there's no custom code that you've written that you need to manage and that you need to operate in that integration, and your service can then just pick up from SQS. So if your service was to go offline, or for some reason your service over here had a network problem, all that's going to happen is all these items are just going to build up in the queue, and once your service comes back online or the network's fixed, then you can just process from where you left off. And if you're using FIFO queues, that is processing where you left off exactly in the order that you did. any of these services can also be replaced with Eventbridge. So Eventbridge also integrates directly with SQS. So by the same way, you could publish an event onto Eventbridge and have a set of SQS queues as the subscribers instead of using your actual custom code as subscribers. So on the subject of custom code, so what I've covered so far has been orchestration and choreography and all these kind of native services that stitch together really nicely. But at some point, you're going to have to write some code to implement your business logic. You know, the value that you're bringing to your customers is going to come from code. And that's where AWS Lambda comes in. So I'm sure most people who are familiar with AWS have heard of Lambda in one way or another, but Lambda's biggest superpower, especially when it comes to event-driven architecture, is it's completely event-driven. So Lambda reacts to other things that are happening in a system. And Lambda lets you run your code without provisioning or managing servers. And you only pay for the compute time that you consume. There's no charge when your code isn't running. And that compute time is charged to a per millisecond basis. And that per millisecond charge scales up based on the amount of memory that your function requires. It's important to point out, I always like to point out here when I talk to customers, is that as you increase the memory allocated to your function, which is a greater per millisecond cost, that doesn't necessarily mean you're going to have a higher cost for running that Lambda function. You know, if you increase the memory, but it runs in half the time, it's probably cheaper to have the higher memory, which might not seem obvious at the outset. And there's tools out there that can help you automate that discovery to find the right balance between cost and performance. And with Lambda, you can run code for virtually any type of application. You know, I've seen people use it for simple batch scripts right through to machine learning workloads. You know, customers are actually starting to run machine learning workloads with Lambda, and all with absolutely no administration of the server, and all with a really great cost. And Lambda can integrate with lots of other AWS services, so like SQS, step functions, API gateway as a front-end API, Eventbridge. All of these services integrate natively with Lambda. So with the queue example in mind, if you were running your own queue, you need to write some code to manage the polling of that queue and the deleting of items from that queue. Whereas if you're using SQS and Lambda, the Lambda service actually handles the polling of the queue, and the Lambda service just passes events and messages to your code. And as providing your Lambda function completes successfully, the Lambda service will then also manage deleting the records from the queue as well once they've been processed. So it's just a really powerful integration. And Lambda does support Java as a natively managed runtime. So that means a lot of the existing code that you might have in your applications now can be relatively easily moved into Lambda with a little bit of refactoring normally required to meet this event-driven paradigm. So one thing I always get asked when I talk about Lambda is cold starts. People always talk about cold starts, and they are quite a big thing with Java and .NET as well. So to explain a little bit about what a cold start is, so the way Lambda works is that when a Lambda function is invoked for the first time, or when it's scaled, a new execution environment is created. And the first phase in that execution environment's lifecycle is what's called the initialization, or the init phase. Now for Java, in that init phase, a new JVM started up, and then your application code's loaded. And that's what's called a cold start. And that's where you commonly see a slight delay the first time you run a Lambda function. Now, subsequent requests that come in can then reuse that same execution environment. And these execution environments do hang around for a little while. If you look around the internet, you see things from 5 minutes to 15 minutes to 60 minutes. There's actually no SLA from the Lambda service team for how long an execution environment will stay around for. But they do stay around for a little while, and they are reused from function invocation to invocation. Again, the second time a request comes in, that init phase doesn't need to happen again. So that's then called what we call a warm start, because there's an environment always available. Now, that init phase, especially for the JVM, can be quite a slow process. Now, for like an asynchronous, maybe a queue processing function, that's not so much of an issue because you don't need that low latency. But if you're using Lambda for example, a front-end API, that obviously is quite a big problem. So a colleague of mine's actually stole a hot take I had for you as part of this presentation, but there's an improvement that's just been released to Lambda last week, and there's a blog post gone live maybe half an hour ago. That's the bottom link you can see on the screen, and that's a change to the execution environment to introduce tiered compilation. And you can turn that on just by setting an environment variable as part of your Lambda function. And what we're seeing with that tiered compilation is up to a 60% performance improvement for cold starts compared to the standard JVM. And that's a pretty big improvement just from adding an environment variable, and to anything that can be done to lower this cold start time is really beneficial for Lambda, especially with, like I said, Java or .NET as runtimes. There's a couple of other links there, and I will put these in the Zoom chat after I've done with the presentation, to a couple of GitHub repos. And they're repos that cover a whole bunch of different ways to run Java on Lambda using things like Spring Boot or Micronaut or the GraalVM. And there's some really interesting performance improvements that come once you kind of move away from the Java managed runtime, which the Lambda service team are building to support a wide variety of use cases. And you can really start to really get a really good cold start improvements as you start to tweak how you actually use Java on Lambda. So just to summarize everything I've talked about so far, I just wanted to go through some key benefits that I see when you start to introduce event-driven architectures. And the big one is your developer efficiency. And there's two parts to this. So the first part is when you're building a new feature or a new service, you can discover what events are available easily using EventBridge and Schema Registry. You can generate code bindings directly to your IDE from them events, and you can really quickly start to build new services and new functionality without worrying about interfering with your existing code, because it's all completely standalone, all completely decoupled, and you can almost do what you want relative to the rest of the system. You can then also start to publish events back into the system once your service is running, and they'll then appear in the registry that other teams can then easily start to hook into and start using to enrich their systems. And the second benefit I see from a developer standpoint kind of goes back to what I talked about right at the start about how humans like stories and we like to rationalize about things. You know, if you imagine you're talking to a business person who actually needs a business requirement from the software you're building, if you can talk about your software that you've written as a developer in the context of events, you know, what do you want to happen after an order is created? What do you want to happen after an order fails or a payment fails? And it really opens up these lines of communication to business people who are used to dealing in events. They're used to, they might not talk about them quite that explicitly, but they're used to wording things in that way and thinking about things in that way. You know, if this thing happens, what do I want to do next? And that again is really powerful for your developers. You know, the closer you can get your developers to your business people, the faster and more efficient that the software development process will be. And the second benefit is loosely coupled services. I know I've probably been banging on about loosely coupled services for the last 40 minutes or so, but it's such a powerful thing when you're building large scale systems, is to keep things as decoupled and as independent as possible. So all the services are interoperable, and if one service has a problem, the rest will keep running. And especially if you're using that SQS again as an example, any service that's offline, the queue will just start building up with items and building up with items, stored durably. And once that service comes back offline, it can just keep processing from where it left off. And that is really powerful because it allows you to scale independently. You can accommodate for surges in your workloads with the queues because the throughput of a queue is really high. And it just really helps to negate some of the problems that come with distributed computing at really large scale. Because any computing in the cloud, when it comes down to it, is distributed in some way. The third point is it allows you to audit and also observe your systems with ease. So when you've got this centralized event router, you can actually have policies and permissions to EventBridge to maybe say, you know, only certain systems can get certain events. So as you've got them a centralized place to control how these events flow around the system, and you can determine which users have access. And then with the schema registry and the archive and replay functionality, it actually allows you to observe your system with ease. So you could go in and observe, say, a step function workflow, and you could see on the graph how that workflow ran. You could then go and look at EventBridge and find the archive of that event that was published, and then you could actually replay that event, and then you could follow that downstream and see what happens. So it makes observing and auditing and kind of debugging really edge case scenarios, I don't want to say easy because everyone knows that's not easy, but easier to kind of identify what's happening. And then the final one, where when I talk to business people and not developers, their eyes kind of light up, is cut costs. So because event-driven architectures are reactive, your system's only working when it absolutely needs to. And with Lambda, that's to the millisecond your build. That really can help to reduce your costs. You know, there's no network bandwidth consumption, there's less CPU utilization, you've got less servers sat around doing nothing really for a lot of the time, and maybe only being there ready for the spikes in workloads. And the kind of to spin the cost in a kind of sustainability way as well. You know, if you're using to the millisecond the compute you need to, you're not using power and you're not using electricity when you don't need to, running a server that might only be running at 20–30% capacity for the vast majority of the time. So just to kind of round out now, I always like to end these kind of presentations with something tangible that you can take away and actually use. So the first thing I would say is, if you're not already, start publishing events. You know, introduce some kind of centralized event location to your current system, and just start to add events. You know, where interesting things are happening in your system, just publish events, and that then starts to build up this store of events. And then maybe look at your feature backlog and look at what features could we add where we could maybe decouple that a little bit, or we could run that as an independent service. Identify that feature, and then maybe build a small team of developers who can maybe build a proof of concept, say what would happen if we built a service using an event-driven architecture. And you can use that as a proof of concept, and because it's so small and decoupled and independent, if it doesn't work, you can then maybe merge that code into your existing code base. But it allows you to move really quickly and try out new ideas. And with that, I will say thank you for listening. I appreciate you all joining me on your lunch break and listening to me talk about pizza for 40 minutes. I've put my Twitter and my LinkedIn on the page there. I'm more than happy to chat offline if anybody's got something they don't want to ask now. But yeah, if anybody's got any questions, or if there's anything that's come up in the chat, then please feel free to unmute and reach out, or put something in there. And I'm just going to stop sharing my screen so I can actually see what is happening.
A huge shout out to James for the great presentation. I'm just going to read, we had like one question during the presentation. If anyone else has any questions, James, do you have a few minutes to answer some questions?
Yeah, absolutely.
So type in and I read it to James. So the first question was from Dinuk. I hope that I got it right. Basically, there is a difference in mindset when talking about event-driven and message-driven architectures, right? So what would the like mindset changes be between the two approaches? And also, he said that he couldn't find a lot of material to address the when or when not to use each one of those architectures, right?
So I'm not intimately familiar with message-driven architectures, but from what I do know about them, the two are very similar. You know, fundamentally, you're switching how you think about your application or your system to be driven by a message or an event or something that's happened in your system. Yeah, I'll see what I'll do. I'll see if I can dig out some more material on that, and if I can send that maybe via you, Anthony, or you can put a contact details in the chat. I can pass that on. But yeah, like I said, the two will be very similar in a sense that you're kind of switching your thinking to be less about method calls and databases and data, and more about events and interesting things that are happening in your system.
Okay. I think that I'll ask a question of my own. Feel free to tell me that it's out of scope, but you spoke a lot of EventBridge, SNS, and SQS, but like AWS is so big and there are so many things that always overlap, right? So I don't know, I use Kinesis that had the like data streams.
Yeah.
There is Manage, Kafka. So in the same kind of question, is there like some place that I can, I don't know, read it? Okay, I need to do X, use those technologies, you know, like how they compare and overlap.
Yeah, so the way I commonly think about that is based on what you're building. So if I were building a greenfield application that was brand new, I'd be moving more towards your SQSs, your SNSs, your event bridges, your managed service, because the benefit of them is that they're completely serverless. AWS get rid of all that management that you need to do. Whereas if you're already using Kafka, maybe on premise, or you're using RabbitMQ as the example from the presentation, then you might look at something like MSK, which is the Amazon Managed Kafka, because that then allows you to not need to change your application code so much, but you can still then start to leverage some of the benefits that come from having AWS manage at least a portion of your infrastructure. So that's, and then once you kind of get that split, the services do kind of have different things. So like Kinesis is for streaming data, SQS is for queues, EventBridge and SNS is the one that's where I cover it in the presentation, because that's the one where people commonly say, oh, they're the same service. So, and there are some trade-offs between both SNS and EventBridge. Whereas if you go down the other route and you're using maybe some open source software already, then again, there's some quite clear Kafka or RabbitMQ or hope that answered your question, Anthony.
Yeah, it did for sure. So we had a couple of more. So the Dafit or Dafit, I don't know if I got it right again, said that event-driven architectures are for processing records or things that have already happened. For instance, they should not have been used to decide what happens next. Is that the right way to think about it?
Kind of, yes. So event-driven architectures, so events are the way of your services communicating with each other. So an event would be how one system maybe notifies another system that something has happened, but then the service that's consuming that event will probably choose to do something based on that event. So going back to the example from the presentation, if the order management services produces an order created event, then there's some services that might not actually care about that and they'll just ignore it. But the kitchen service, the service that's actually going to produce the pizza, that would need to care about it, and that would then choose to do something next. So yeah, for the consumers, yes, they're going to use that to decide what to do next. For the producer, you're just telling the world about something that you've just done.
So Dale has a question. What's the rough time between rolling your own versus using like a step function, basically? So what's the time effort comparison between using step functions versus doing everything by yourself?
Yeah, so just put a quick yes in the chat, or say yes, unmute and say yes, Dale. But when you say hand rolling it, do you mean like building like a workflow from scratch using custom code? Yep. Yeah, so it's hard to put a time on that, because it would depend on the complexity of the workflow. But what I will say is that things like retry logic and exponential back off, and how often you want to retry and handle errors, step functions kind of does all that natively. Whereas trying to roll your own, I know there's libraries out there that can do it for you, but trying to integrate your own, to build your own workflow engine that handles all that kind of stuff, I've found, at least trying to do it myself, it's quite difficult sometimes. Whereas, if you've got a service that can handle all that complexity of retries and monitoring and observability and state management, then I'd estimate that the time effort will be a lot lower to use step functions as it would be roll itself, especially now. So if you'd asked me that maybe 6 months ago, I might have given a slightly different answer, because the Amazon state language of the ASL that you use to define the workflows is, it can be quite complicated to pick up. But now that they've released the Workflow Studio, where you can actually build a workflow in drag and drop interface, it's all a user interface, and then you can export that has massively decrease the amount of time it needs to create a workflow, because you're literally just dragging and dropping building blocks, putting them together.
That's a great answer. So I think that's a follow-up on the last one as well. So networks of step functions are essentially a way to integrate service with serverless state machines. Exactly. Is that it?
Exactly, yeah.
Okay, so that probably answers the Michael Baterman. Is this just a finished state machine effort? So yeah, I think that's everything for the day.
I will just call out, actually, I just noticed that Andrew's talked about eventual consistency and scale considerations. So yes, eventual consistency is a really great call out. I should probably add that to the deck, actually. But yes, so because once everything becomes distributed, eventual consistency is something that you do need to think about. So for anyone who isn't aware of what eventual consistency is, so if it's easy to talk about it in the context of a database. So if you're using transactions in your database, you can have a strongly consistent write to your database, because you've wrapped that in a transaction. You know that write has happened there and then. Whereas an eventual consistency is more like a bank statement, actually, is an example I commonly use to describe eventual consistency, where you've got like a pending transaction in your bank statement. So that's a transaction that you know that's going to happen and get committed to your bank statement at some point in the future, but you don't know exactly when that's going to be written. So yeah, you do need to think about that, and there is a trade-off, absolutely, Michael. And then scale considerations. So because you've got all these decoupled services now, and if you introduce something like SQS, it does allow you to scale really easily, because you can write all your records to SQS, and then you can add more receivers or less receivers, or however many receivers you need to process the load as it comes in. So it does allow you to scale really easily because of how decoupled everything is. Everything can just scale independently as and when it needs to.
Fair enough. Again, James, massive shout out. It was a great presentation. So James has shared his contacts already in the chat, and
Before we just close I'll just put these links from the presentation in the chat so that people have got them.
Fair enough. Yeah. And the presentation is being recorded. I probably should have said that during the beginning, but yeah. Abby will make a link available in YouTube. You can reach out directly to her. And yeah, thanks, James. It was fantastic. Anyone has any last minute questions or? No.
Great. Well, thank you for hosting that, Anthony. That's been, yeah, really good. Thank you. And thanks everyone for taking the time out and listening. Go and grab a pizza. No, I don't forget about pizza. I know I'm going to.
Cheers, everyone. Enjoy your lunch and your afternoon.
Thank you, everyone.
Bye.